Welcome to the Amateur Radio Foundation License Training. This second training will be about technical basics in the hobby. We'll be discussing units and symbols, voltage, current, resistance and circuits, conductors and insulators, formulas, frequency and wavelength, and digital signals. There are several units in science that help us to measure and quantify values, and this table shows the ones that you need to learn for the foundation license. We have here voltage. The symbol for voltage when it's written is a capital V. It's measured in something called volts, same as we would measure miles for distance, and the units are also volts. So if you work out a calculation and it ends up being 10, it would be 10 V, 10 volts. We have current. The symbol is I, which is a bit unusual. You'd expect it to be A, but A is used for other things. They're measured in amps, and the units are amps, so you would have 10A or 10 amps written out. We have resistance. The symbol is a capital R. It's measured in ohms, and the units would be in ohms as well. And ohms are a capital omega Greek symbol. We also have power, capital P, measured in watts, and a capital W for the units. Frequency is a lowercase f, measured in hertz, and the units are H, capital, and small z. And then finally wavelength. Wavelength, the symbol is a lambda, measured in meters, and the units are a lowercase m. So when we're writing out units in a calculation, we can end up with very, very big numbers or very, very small numbers, and in order to stop us having to write zeros forever or 1, 0, 0, 0, 0, etc. We use an abbreviation, if you like, as follows. So we use the word micro, which means 1/millionth of something. The decimal longhand is 0.000001. The prefix is a mu symbol, which is like a U with a long leg on the left hand side, and an example 1000 microvolts, as you see there. We also have milli, which means 1000th, which is in decimal 0.001. The prefix is m, lowercase, and as you see in the example, 1 millivolt would be a lowercase m and a capital V for volts. We then have kilo, which we should all be fairly familiar with, is 1000. Its prefix is a lowercase k, and in the example there, 2000 would be written as 2k. We have mega, which is 1 million, and that's a 1 and 6 zeros. Its prefix is a capital M, and it's written as a capital M and then the units, so 3 capital M for mega, and then hertz, for example, would be capital H, lowercase z. And then finally for this course, giga. Giga is 1000 million, a capital G, and I'm sure you've probably heard gigahertz to do with computers and Wi-Fi, so it would be a capital G, capital H, and a lowercase z. So please become familiar with these, practice them, practice writing them out, practice the prefixes, and do remember some are capital, some are lowercase. A capital M, for example, could mean mega. A lowercase m is milli, so that's a long distance away from each other to get it wrong by simply putting a capital or not. So moving on, we're going to learn several electrical symbols. We have a symbol here for a cell, and a cell is a single battery. If you imagine you have AA batteries that go in your remote control, One of them is actually called a cell. Multiple cells are a battery. So in a device where you have multiple cells, you would have a battery. If it's a single cell, a single AA battery, we call that a cell. So if you look at the symbol here, we have a longer line and a shorter line, and the longer line is the positive side, the shorter line is the negative side, and we'll go into that more later. The battery, as you can see there, is two cell symbols joined together, and again on here they've notated the positive and negative sides of the battery. We have a lamp or bulb, which is a circle with a cross through it, very straightforward. An LED, and this is an unusual symbol, it's a triangle with a bar across, and usually it has these two little arrows indicating that it's giving off light. We also have a symbol for a microphone, which is a circle with a bar on one edge, and it kind of looks like a microphone, so generally that's easy to remember. We have a speaker, likewise it's a box with a cone on it, so it does look like a speaker, fortunately. And on the bottom row here we have the antenna, which looks like a chicken's footprint. We've got the earth symbol, which is three horizontal lines. We have a resistor, which is a rectangle. A switch, which is two circles with a bar in the open position. And finally a fuse, which looks like a resistor, but the line goes straight through it rather than stopping at each end. Again, please practice these, drawing them out, and just become familiar with them. Next, we're going to describe current. The flow of electrons in an electrical circuit is known as the current. So if you picture water flowing through a tube, this is the kind of idea to get in your mind. And this current is measured in amps. And please remember, a thicker cable has a higher capacity to carry current, and therefore thicker cables allow more electron flow and therefore can carry a higher current. Electrons are a charged particle that flows through substances, and if you picture it as balls flowing through a tube, that's probably the best way to think of it. But in essence it's like water flowing through a tube. It's a flow of electrons. With conductors and insulators, a conductor allows electrons to flow easily. An insulator does not. It's the opposite. It resists flow. So examples of conductors are things generally metal like copper, brass, silver and gold, and carbon as well. For insulators, the materials normally used are plastics, wood if it's dry, rubber, glass, ceramics, that type of thing. So please familiarise yourself with these examples. There may be a question on the test about this. And again, a safety note there, water is a conductor and current can flow across wet insulators. So the insulator itself might not flow electricity, but the water wetting it will. So that can be dangerous if you're not thinking about it. Next, we're going to talk about batteries. A battery is a combination of cells, usually in series, which means end to end. This provides electrical energy from stored chemical energy and has a potential difference or voltage, which is measured in volts, across its terminals. A primary battery is not rechargeable. Once it's discharged, it must be properly disposed of. And this is what we think of the typical battery, a non-rechargeable battery. Once it's used, it's disposed of. A secondary battery is a rechargeable battery, and its chemical process inside is reversible, so we can recharge it back to the full voltage. Circuits. This basic circuit shows a lamp being powered by a battery. A circuit is needed to allow current to flow. A current includes a source of electrical energy, such as a battery. The polarity, the positive and negative sides, must be correct for some components to work. Incorrect polarity may cause damage as well. Direct current. The battery in this circuit provides DC, direct current, volts. Current flows in one direction from the battery to the light, and just be aware that in paperwork, voltage is sometimes referred to as potential difference. It means the same thing. Potential difference and voltage are interchangeable. Alternating current. Direction of current flow constantly alternates between positive and negative. The UK mains voltage here is 230 volts at a rate of 50 Hertz. So this means that it goes positive and then back to negative and then back to positive and back to negative. It oscillates in this manner 50 times every second. So this is alternating current that powers our houses. So the next slides are going to continue on with formulas. The first one is power. Power is measured in watts. The calculation for power is voltage multiplied by current. We draw a diagram here of a triangle with the letters in this particular orientation, the P at the top and the V and I below. In the exam, you may be asked to calculate power, voltage or current using this formula, where they will give you two of the known values and you calculate the third. As you can see on the left of the slide here, power is equal to the voltage multiplied by the current. We can use the triangle to remember this by covering what we are looking for, which is the power, with our hand, and you'll notice that V and I are the only letters left visible. Because they are on the same line, we multiply them. So power, which we're covering, equals voltage multiplied by current. If, for example, we would like to calculate the voltage, and they give us the power value and the current value, because we want to calculate the voltage, we cover the V with our hand, and that remains the P over the I. So imagine the line between them being a dividing line, P divided by I. We can calculate the value of the voltage by getting the power value and dividing it by the current value. The final calculation would be to calculate the current. And in order to calculate the current, we'll follow the same procedure. We will cover the I with our hand, which left visible the P over the V. So we know that we divide the P value by the V value. So for example, 10 watts divided by 2 volts. 10 divided by 2 would give us 5 amps. Current is measured in amps. So again, please practice this a few times just to get the hang of it, and you'll find it very easy to do these calculations during the test itself. We're going to do an example here, a calculation using the triangle. A 60 watt speaker runs on a 12 volt battery. What is the current? So we cover the I, as we previously described on the triangle, and that leaves us with P over V, P divided by V. So we write 60 watts, which is the power value, divided by 12 volts, which is the voltage value. And when we put that into our calculator, we will find that 60 divided by 12 is 5. So we can then write the answer 5 amps. And this works for every combination, whether it's voltage, power or current we're trying to calculate. Next is resistance. Resistors are components that limit or oppose the flow of current. They slow it down. They decrease it. This is measured in ohms, and the symbol you see there is the omega, which is the symbol for resistance. In this circuit, a resistor R will cause the lamp to be dimmer or not to light at all. What this means is instead of getting the full power of the battery, it's actually going to lower the power and therefore make the light dimmer. And it does this by restricting the current. A current through a resistor results in conversion of electrical energy into heat. So by slowing down the current, it's causing, if you imagine, friction, and therefore it's slowing the flow and getting hot instead. This is where the energy goes to. So it goes from a flow of current into heat instead. You'll notice the picture of the resistor at the bottom there. It has coloured bands on it, and this is signifying the value of resistance of that particular resistor. Next, we're going to describe another calculation, and this is called Ohm's law. This is also easily worked out via the triangle, and in this triangle we have V at the top and I and R below it. It works in exactly the same way as the power triangle. So by covering the letter that you want to calculate, it shows you what to do with the other two values, whether it's multiplying or dividing, as we've said before. We'll go through an example now. So a radio has a resistance of 24 ohms and needs a current of half an amp. What is the voltage? So because we want to calculate the voltage, we'll cover the V with our hand, and we end up with I times R. So we put the numbers into that, half an amp times 24 ohms, and this gives us a value of 12, and it's 12 volts because it's voltage that we're calculating. If you have any questions about these calculations or you get stuck, please come and see one of the tutors, and they'll be happy to give you some examples and help you along with it. Next, we're going to discuss series and parallel circuits. In series, the current passes through one lamp and then to the other. The current passing through both lamps is the same. It's one path, and therefore it has to be one equal flow throughout. This top diagram on the right, as you can see, shows arrows of the flow of the current, and you'll notice that it goes from the battery to the first lamp, then to the second lamp, and then back to the battery. It's like a road, a racing circuit, and there's no turns available. You go round in a circle and there's no left or right to give you options. You're just going round the same way all the time. The voltage required for the circuit is the sum of the individual voltages across each lamp. So by taking a measuring tool and measuring either side of lamp 1 and then again of lamp 2, when you add up those voltages, it should give you the voltage of the battery. Next, we're going to discuss parallel circuits, and in the lower diagram you can see that current can pass through both lamps individually. It can go through the first one only, the second one only, or both. And in reality it will always go through both. The same voltage passes through both lamps. So the voltage of lamp 1 will be equal to the voltage of lamp 2, which will be equal to the voltage of the battery. All three voltages will be identical. The current required is the sum of the current going through each lamp. So the total current is the current through lamp 1 plus the current through lamp 2. So here's an example. Let us assume that each lamp is the same and needs 3 volts to light it up. If we have a series circuit, the battery voltage required is 6 volts. we will have 3 volts dropping across the first lamp and 3 volts dropping across the second lamp. So 6 is required total to keep them both lit. If one lamp blows, the whole circuit stops because we've made a break in the circuit and therefore the current cannot flow all the way round. In a parallel circuit, we can look at the lower diagram, and the battery voltage only has to be 3 volts because in a parallel circuit, as mentioned before, lamp 1 equals lamp 2 equals the battery. All 3 items have the same voltage across them. So you can run a parallel circuit at a lower voltage and still light both lamps. The current is halved across the 2 lamps. So the total current is divided between the 2 lamps, and if the 2 lamps have an equal resistance, the current will be divided equally. So you'll have half the current through one lamp and half the current through the other lamp. If one lamp blows, the other lamp will still continue to shine because the current can go through one lamp without having to go through the other. Next, we're going to discuss digital signals. Analog signals are constantly changing in amplitude. This is the height and the depth of each peak that you see on the picture there. They can change in amplitude, as we've mentioned. They can also change in frequency. They can go up and down quickly or slowly. And the amplitude and frequency can change independently or both together. Digital signals are a stream of finite values at a specific sampling interval. Digital signals are better at overcoming noise and require a computer processor and suitable software to read them. So, analog and digital conversion. Digital signals are processed by a computing device. An analog to digital converter samples an analog signal and produces a digital representation of that analog signal. If we look here at the diagram, you'll see the wave, which is the analog signal. The computer will assess that and give a representation in digital form. And digital form is a mix of zeros and ones. Imagine a light switch, it's either off or on. So digital is like switching a light switch on and off to try and mimic the analog signal. A digital to analog converter represents a digital signal in analog format. So this is the opposite. Instead of having an analog to digital, you can also have a digital to analog. So this converting process can go either way depending on what you want to do. Next, we're going to discuss frequency and wavelength. Frequency is represented as a sine wave, which can be generated by an oscillator. This can represent a radio frequency or an audio frequency. And this is an analog signal. During the test, you'll be given a frequency to wavelength conversion table, and it will look like this. We saw this in the last course, the last set of slides, and it will give you the wavelength values on the left and the frequency in megahertz on the bottom, and you can just follow the lines up and across or across and down, whether you're converting from wavelength to frequency or frequency to wavelength. You're simply reading it off the chart. If you have any questions about this or you didn't understand it from the last training, then please ask one of the tutors. As a general rule, with frequency, as the frequency gets higher, the wavelength gets shorter, and vice versa. If the frequency gets lower, the wavelength becomes longer. And again, this table chart that you see here is provided in the exam. So we're going to discuss frequencies now. there are a few facts that you need to remember for the exam. The first one is that the mains frequency in the UK that provides houses with power, the frequency itself is 50 Hz. Audio frequencies, so these are noises that we hear through our ears. The frequency of those noises ranges from 20 Hz to 15,000 Hz. So we can hear things as low as 20 Hz and as high as 15,000 Hz. Remember, that's 15,000 oscillations per second. Audio communication generally is between 300 and 3,000. So when we talk to people, our voices, as they get higher and lower, range between 300 and 3,000. So a much narrower range than our actual hearing range. Radio frequencies, however, are much higher than this. The frequency range for radio frequencies can be as low as 30,000 Hz to beyond 3,000 million Hz or 3,000 megahertz. The general bands that we will use as amateurs are the HF band, which stands for high frequency band, and these run between 3 million Hz to 30 million Hz. Again, 3 megahertz to 30 megahertz. The VHF band, which stands for very high frequency, runs from 30 megahertz to 300 megahertz. And the UHF band, which is ultra high frequency, runs from 300 megahertz to 3,000 megahertz. So as you can see, radio frequencies are much, much higher frequency than what we can hear, and again what the mains voltage is in a property. All of these facts could be tested during the exam, so please try and commit them to memory, and again, if you have any questions, please contact your tutor. So in summary, we've discussed units and symbols. We need to learn the units and the prefixes, milliwatts, megawatts, gigahertz, all those different options. And we need to recognise the symbols, the resistor, the cell, the speaker, the microphone, etc. In terms of electronics, we've described alternating and direct current and series and parallel circuits. Please review those and try and understand the voltages, etc. Again, it could come up in the exam. With formulas, we've discussed power equal to volts times current, and Ohm's law, which is volts equals current times resistance, and we drew out the triangles that represent those calculations. Again, learning that simple triangle will make doing the questions in the exam much easier. We discussed digital signals, converting from digital to analog and vice versa, and we've discussed frequency versus wavelength. So as frequency rises, wavelength reduces. So that's the end of the technical basics set of slides. If you have any questions, please contact us and get your questions answered. And please revisit all these topics and do a bit of practice so that your understanding is solid.